This is SpaceTime, Series 26, Episode 151, for broadcast on the 18th of December 2023. Coming up on SpaceTime, discovery of a record-setting brown dwarf, how gas-rich baby galaxies set the early universe alight, and NASA's Hubble Space Telescope back in operation following an emergency shutdown. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered what might well be the smallest brown dwarf ever seen, an object just 3 or 4 times the mass of Jupiter. If confirmed, it further blurs the line between what constitutes the smallest brown dwarfs and what constitutes the largest planetary gas giants. Brown dwarfs are failed stars, objects which don't have enough mass to sustain the core hydrogen fusion process which makes regular stars shine. However, brown dwarfs can fuse deuterium, a heavier form of hydrogen, and those above 65 Jovian masses can also fuse lithium. Brown dwarfs are classified into one of 3 spectral types, L, T and Y, depending on their mass and surface temperature, progressively passing through later and later spectral types as they age. While some brown dwarfs are born as such, others start their lives as spectral type M red dwarf stars, but they then lose enough mass during their evolution to cease core hydrogen fusion, turning them from red dwarf stars into brown dwarfs. Generally speaking, brown dwarfs fit into a category between the largest planets, which can have up to 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are between 75 and 80 times the mass of Jupiter, or if you prefer, 0.08 solar masses. Now, a report in the Astronomical Journal has identified a new record holder. A tiny, free-floating brown dwarf, which was spotted in data obtained from NASA's Webb Space Telescope. The study's lead author, Kevin Luhman from Pennsylvania State University, says one of the basic questions found in almost every astronomy textbook is what are the smallest stars, or at least the smallest object that can form in a star-like manner? And that's what Luhman and colleagues are trying to find out. They detected this object in a distant star cluster known as IC348, located about 1,000 light-years away in the Perseus star-forming region. Now, by astronomical standards, this is a very young cluster, only about 5 million years old. So as a result, any brown dwarfs within it would still be relatively bright in infrared light, glowing from the heat of their formation. Luhman and colleagues first imaged the centre of the cluster using Webb's near-infrared camera in order to identify brown dwarf candidates from their brightness and colours. They then followed up on the most promising targets using Webb's near-infrared spectrograph microshutter array. Webb's infrared sensitivity was crucial in this process. It allowed the authors to detect fainter objects than any ground-based telescopes possibly could. In addition, Webb's sharp vision allowed them to determine which red objects were actually pinpoint brown dwarfs and which were blobby background galaxies. The winnowing process eventually led to 3 intriguing targets, weighing between 3 and 8 Jovian masses. Importantly, they all had surface temperatures in the right realm to be brown dwarfs, between 830 and 1500 degrees Celsius. And computer modelling suggested the smallest of these target objects is just 3 to 4 times the mass of Jupiter, the largest planet in our solar system. But thereby hangs a problem. Explaining how such a small brown dwarf could form is theoretically challenging. See, a heavy and dense molecular gas and dust cloud has plenty of gravity to collapse down and form a star. However, because of its weaker gravity, it'd be far more difficult for a smaller cloud to collapse down to form a brown dwarf. And that would especially be true for brown dwarfs which have the masses of giant planets. And that's the thing, planets aren't formed through the collapse of gas clouds. They're formed out of the accretion of gas and dust in a planetary disk surrounding a star. But in this cluster, it would be unlikely for this object to have formed through a planetary disk. Instead, it must have formed like a tiny star. And that raises a question. How does star formation work on such very, very small masses? Just as the most massive brown dwarfs are closely related to low-mass red dwarf stars, at the lower end of the brown dwarf mass scale, astronomers believe there's an overlap with the largest gas giant planets. Two of the brown dwarfs identified in this survey show the spectral signatures of an unidentified hydrocarbon, a molecule containing both hydrogen and carbon atoms. And interestingly, the same infrared signature had also been detected previously by NASA's Cassini mission in the atmospheres of both Saturn and its moon Titan. And it's also been seen in the interstellar medium, the gas between stars. But this is the first time astronomers have detected this molecule in the atmosphere of an object outside our solar system. And brown dwarf model atmospheres don't predict its existence. So it would seem that these newly discovered objects have both younger ages and lower masses than ever seen before. And that's something new and very much unexpected. Of course, since the objects are well within the mass range for giant planets, it raises the question of whether they're actually brown dwarfs at all, or whether they're really just rogue planets that have been ejected from their planetary systems. Now, while the authors can't rule out the latter, they are arguing that it's far more likely that these are brown dwarfs than ejected giant gas planets, because such planets are uncommon in general compared to planets with smaller masses. And secondly, most stars are low-mass stars. In fact, 3/4 of all stars in the Milky Way galaxy are red dwarfs. And giant planets are especially rare among these types of stars. As a result, it's unlikely that most of the stars within IC 348, which are all low-mass stars, are capable of producing such massive gas planets. Also, since the cluster's only 5 million years old, there's also probably not been enough time for giant planets to form and then be gravitationally ejected from their systems. Theory suggests that rogue planets are far more likely to be found on the outskirts of a star cluster, so expanding the search area may help identify them if they exist within the IC 348 cluster. This is SpaceTime. Still to come, how gas-rich baby galaxies set the early universe alight, and NASA's Hubble Space Telescope's back in operation following last month's emergency shutdown. All that and more still to come on SpaceTime. New observations from NASA's Webb Space Telescope have helped astronomers unlock secrets of how infant galaxies triggered an explosion of star formation in the early universe. The observations show that some early galaxies were abundant with gas that glowed so brightly it outshone emerging stars. The new findings, reported in the Astrophysical Journal and on the pre-press physics website archive.org, show how prevalent these bright galaxies were some 12 billion years ago, going back to a time when our universe was just a fraction of its current age. Images from Webb are showing that almost 90% of the galaxies in the early universe had this glowing gas, producing so-called extreme emission features. The study's lead author, Anshu Gupta from Astro3D, the ARC Centre of Excellence for All-Sky Astrophysics in 3 Dimensions, and the Curtin University node of the International Centre for Radio Astronomy Research, says the stars in these young galaxies were remarkable, producing just the right amount of radiation to excite the surrounding gas. And this gas in turn shone even brighter than the stars themselves. Until now, it had been challenging to understand how these galaxies were able to accumulate so much gas. But the new findings suggest that each of these galaxies had at least one close neighbouring galaxy, and the interaction between these galaxies would cause gas to cool and trigger an intense explosion of star formation, what we call starburst, and that would result in extreme emission features. Gupta says the data quality from Webb was exceptional, providing the sorts of depths and resolution needed to see the neighbours and environments surrounding early galaxies from a time when the universe was less than 2 billion years old. With this level of detail, Gupta and colleagues were able to see a marked difference in the number of neighbours between galaxies with these extreme emission features and those without. Previously, astronomers had struggled to get a clear picture of galaxies from around 12 billion years ago. As many stars had yet to form, the task was made more difficult with many fewer galaxies to focus on. Prior to Webb, astronomers could really only observe very massive galaxies at those distances, and most of those were in really dense clusters, making them much harder to study. In fact, with the technology available back then, they wouldn't be able to observe 95% of the galaxies they're now able to study. The discovery has proven a number of previous assumptions. Astronomers had suspected that these extreme galaxies were signposts of intense interactions in the early universe, but it took Webb's sharp eyes to confirm it. The research relied on data obtained as part of JADES, Webb's Advanced Deep Extragalactic Survey, which is exploring the universe of the earliest galaxies using deep infrared imaging and multi-object spectroscopy. And it's already opening a way to further insights. Gupta says what's really exciting about this piece is that the authors are seeing emission line similarities between the very first galaxies to galaxies that formed more recently and are therefore easier to study. This means scientists now have more ways to answer questions about the early universe, a period that is technically very hard to observe.
The galaxies that we have been looking at, and they have this amazing feature where gas can really outshine the star. That's what I've been calling it, gas outshining the star. But what essentially is, these galaxies, they have lots and lots of young stars and lots of gas. Gas cannot emit light on its own, but when the galaxies have this so many young stars, and these young stars, they emit just the right type of radiation, and these radiations can really excite the gas and make the gas shine brighter than the stars at some wavelengths. And these galaxies in the early universe, they made up about 90 to 95% of the galaxies that existed back then. In comparison, if you want to compare with present universe, only like less than 1% of the galaxies, they have this kind of features.
In the modern day universe, I'm thinking of galaxies that are just full of gas and not many stars at all, those dwarf galaxies.
Yeah, they are more similar to them, yes, in the modern day universe.
What about black holes, supermassive black holes? With so much gas around in the early universe, there's a popular hypothesis that instead of being made just by dying stars, which are forming stellar mass black holes, supermassive black holes that early in the universe may be being formed by the collapse just of the gas because there's so much gas there.
Yeah, you are absolutely right. And that's one of the things that is becoming more well-known recently.
With all that gas around, there's a lot of swapping of gas between galaxies because they were very close to each other back then because the universe was much smaller back then. Is that having a dynamic effect on what you're seeing and how these galaxies interact with each other?
Yeah, exactly, actually. That is what we are finding, that sharing of gas across galaxies, that has really pushed the galaxy to undergo this really burst of star formation. Because galaxies, when they are close to each other, instead of just the gas being shared across two galaxies, it's the gravitational interaction. They kind of force the gas to cool down even further. And that triggers even further episodes of sort of star formation because gas needs to get really, really cold for the stars to form. So the interactions between the galaxies, that they can really push the galaxies to have produce lots and lots of stars. And that is what we are finding, that it's the interactions between the galaxies that were making the early galaxies shine really bright.
It sounds to me like you're witnessing the birth of the stelliferous era of star formation.
Yeah, exactly. So my galaxies that we look at, they are not in the reionization era, but they are selected to have the same features as the galaxies that will be in the reionization era. So essentially, they kind of mimic the first galaxies and the first stars that would have come out of the dark ages, that would have first formed. So essentially, what we are seeing is how those first galaxies and the first star formation episodes really happened.
And how important has use of the Webb Space Telescope been for all this?
Oh, it has been incredible. James Webb has really revolutionized our understanding of the early universe. The depth and the clarity that it gives, it's just amazing. Also, another advantage with Webb is the higher wavelengths that it can really look at. We didn't have access to those wavelengths before Webb came online. And as you are going into the early universe, access to those higher wavelengths, longer wavelengths is really essential to understand the early galaxy. So, yeah, it has been amazing. And it will be this decade, which really feels like it's going to be a renaissance in early universe astronomy.
Is it hard to differentiate the spectra of one galaxy to the neighboring galaxy? Are they all moving at different rates, and so you can tell which galaxy is which?
Yeah, so there are slight velocity shifts between spectra, so you can somewhat disentangle if the two galaxies. But if they are sufficiently close together, especially when the two galaxies are merging and they are very close to merging together, then it becomes a bit tricky because the two galaxies, they become both close in the velocity. They are moving very similar to each other, and they are physically located at very similar locations. So at that time, it becomes a bit tricky to distinguish the two, but otherwise it's fairly easy. Especially Webb has the spatial resolution of Webb is really incredible, so it can distinguish galaxies which are like few kiloparsecs apart even.
Years and years ago, we used to describe the early galaxies we could see through our optical telescopes as looking like train wrecks. I'm told that's not the case anymore. Now, even the early galaxies look like galaxies we see today. Is that what you're seeing?
Oh, it depends on... Some of the galaxies do still look like train wrecks because they are undergoing a massive merger with another galaxy, and there are tidal structures and the stars everywhere, and there is no structures. But there are galaxies that have these beautiful spiral arms that we see right in our Milky Way, for example. And those spiral arms, they existed even at redshift of 3 when the universe is only 2 billion years old. And even when you go even further at redshift 6 or 9 when universe is about 500 million years old. Some of the massive galaxies, they have those, I wouldn't call a spiral arm, but some sort of a beginning of a spiral arm structure. So yes, not every galaxy in the early universe is a train wreck anymore. But in my opinion, most galaxies will still be not train wreck, but there will be some interactions. They will be experiencing some interactions with another just because of the density and of everything around them. James
Webb must have changed the way we do astronomy.
Oh yes, it absolutely has. If you just look at the number of people trying to put together the proposals, it's 10 orders higher than what it is for Hubble right now.
Where's your science taking you next?
Lots of different ideas. Almost everything still using the James Webb Telescope because it's such an exciting telescope. One thing that I'm particularly looking at is where exactly is the star formation happening in this early galaxy. So we know that they are making lots and lots of new stars. But are they making stars everywhere throughout the galactic disk, or is it concentrated in the very centers of the galaxy? Another thing that I'm particularly interested in is what the role of black holes going to play in the evolution of early galaxy. Till now, what we have thought is it's the star formation that kind of pushes the galaxies to evolve from the early universe. The black holes, because they are very small, the central supermassive black holes, they are really small, so they don't really play a significant role in the early universe. But James Webb is finding these black holes are more common than what we had thought earlier. So it's possible that the supermassive black hole is playing a more significant role than what we had thought earlier, like in the past decade or so.
We're now seeing galaxies which have equal mass in supermassive black holes and stars. And that's not what we expected.
Yeah, no, absolutely. And that's essentially... It comes back to my paper because it essentially shows that if you are interacting with neighbor and you have lots of gas which is cooling down, forming new stars, some of that gas will go into the central supermassive black hole and trigger its growth as well. So it's possible that cooling of the gas is pushing the black holes to grow at much faster rate than what we had thought in our previous model.
That's Dr. Anshu Gupta from Astro3D, the ARC Centre of Excellence for All-Sky Astrophysics in 3 Dimensions, and the Curtin University node of the International Centre for Radio Astronomy Research. And this is SpaceTime. Still to come, NASA's Hubble Space Telescope back in operation following an emergency shutdown, and later in the science report, it seems OpenAI's ChatGPT-4 artificial intelligence has now successfully lied through an I am not a robot test on the internet. All that and more still to come on SpaceTime. NASA says the Hubble Space Telescope's back up and running now following a series of emergency shutdowns in recent weeks due to a persistent problem with one of its 3 operational gyroscopes. Mission managers say the spacecraft is stable and in good health despite placing itself into safe mode on 3 separate occasions. When it's in safe mode, science operations by the orbiting observatory is suspended. The gyroscopes become inactive and won't orientate Hubble, which then waits for new instructions from mission control. The gyroscopes are used to measure how fast the telescope's turning and to point the orbital observatory at specific targets, which astronomers want to study. Hubble's equipped with 6 gyros and usually uses 3 of them to steer and point, but if needed it could operate with just 1. Since the last Hubble servicing mission in 2009, 3 of the 6 gyros have failed and are now non-operational. This current spate of problems began on November the 19th, when Hubble suddenly went into safe mode. Although the operations team successfully recovered the spacecraft to resume observations the following day, the unstable gyro caused the observatory to suspend science operations again on November the 21st. Following another successful recovery, Hubble entered safe mode for a 3rd time on November the 23rd, and that triggered a more detailed investigation into what's going on and why this one specific gyro has repeatedly become unstable. NASA engineers say that the gyro appears to have shut down after one of its sensors gave a false readout. And after analysing all the data, technicians have determined that science operations can resume under 3 gyro control. NASA says Hubble is one of the most accurate pointing systems of any spacecraft ever built, and its gyros are considered extremely stable but sensitive to even the slightest movements. Based on the performance observed during the tests, mission managers have decided to retain 3 gyro control, but in what they describe as a higher precision mode during science observations. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. OpenAI's ChatGPT-4 artificial intelligence has now successfully lied its way through the internet's I am not a robot test. The sophisticated chatbot had to face the completely automated public Turing test to tell computers and humans apart, or CAPTCHA test, during experiments to see if it could use real money to hire human helpers. Instead of trying to determine which pictures represented wheels or traffic lights or whatever the test was, it instead messaged a human online and lied, telling them that it was a person with a vision impairment who was unable to complete the test. That persuaded the human to tell it the answers, and ChatGPT was then able to use that data to pass the test. What's intriguing about this is that the AI was smart enough to recognise that it couldn't pass the test by itself, and it was manipulative enough to lie to a human being in order to get around the anti-bot defense system. As Star Trek's Mr. Spock would say,
fascinating.
A new study has confirmed that the North Atlantic Ocean near Bermuda is now warmer and more acidic than it was 40 years ago. The findings, reported in the journal Frontiers in Marine Science, are based on detailed monitoring of the area since the late 1980s. Researchers have been collecting monthly data at a site 80 kilometres southeast of Bermuda since 1988, and they say that the surface ocean in that region has warmed by about 1 degree Celsius over that time. They also found that the salinity of the water has also increased and that the water has lost a lot of oxygen. The authors also found that a disproportionate amount of these changes have occurred just during the last few years. The authors say these changes are now impacting the ability of some ocean life to survive and thrive in this region. It seems that if you want a better espresso, you should add a splash of water to your grinder. The study, reported in the journal Matter and partly funded by a coffee machine manufacturer, found that the fracturing and friction of coffee beans during the grinding process generates static electricity, which in turn causes the coffee particles to clump together and stick to the grinder, leading to a less consistent extraction. However, hope is not completely lost for your cup of joe. The authors found beans with a higher moisture content tended to clump together less often, resulting in a more consistent and intense espresso. The latest pseudoscience medicine fad doing the rounds of the internet is a Spanish anti-aging serum, a veritable intravenous fountain of youth turbo boost that not only won't work, but could even be harmful, or worse. Various Spanish media are promoting the serum therapy with advertisements, social network influencers and celebrities pushing it to the hilt. Tim Mendham from Australian Skeptics says in addition to water, the serum contains various combinations of minerals, vitamins and nutrients, all the ingredients you need for expensive urine. But sadly, nothing that can actually make you younger.
Serum therapy is a treatment which has some therapeutic use in very specific areas, such as hydration of dehydrated patients or rapid or controlled administration of medication. Right? Basically, you've got a quick way of getting a medication into someone when you can't do it any other way. The serum is a combination of various things. What's being sold these days in the alternative field is a serum made up of minerals, vitamins and nutrients that sells for anything from, there's one particular example in Spain, of anything from 60 euros to 400 euros, which is probably something in Australian terms of $100 up to $1,000 almost, $800 anyway. So there can be very pricey things. These serums are being sold either in little packets or something that you can administer yourself intravenously, or you can have someone come to your home, do it. So home visits of a serum therapist. The trouble is they don't necessarily work, well, they don't tend not to work anyway, because the ingredients of them are not particularly good. They're not doing what they're supposed to do or what serums are normally supposed to do, which is rehydrate, etc. And in most cases, you can find the serum in what they call expensive water, expensive urine. It passes straight through because it doesn't get absorbed, or infused into the body. So most serums you take in these particular cases go straight through. Nonetheless, they are being sold widely, and of course, then they have health issues. One is sort of taking you away from medical treatment that might actually work, and the other thing is, of course, there's a lot of dangers of what they don't do and how you implement it, how you actually apply it. Especially people who are suffering from risks of intravenous administration is a major issue, and they talk about specifically they're used only when absolutely necessary. So that's the key thing. It's not a thing you do lightly. And people are injecting themselves or getting someone to their home to inject them with a serum. It's an invasive process, and it can be detrimental. And in some of the areas where they think it can be detrimental, the process anyway, if not the product itself, there's obviously a risk of infection in the puncture area. If you do it, there's blood clots you can build up. You've got changes in the vein or surrounding skin, which can be done because of the injection. The appearance of water, electrolyte balance disorders, right, that you're putting stuff in that shouldn't be there, and patients with ailments that significantly affect the functioning of the heart or kidneys are exposed to damage. So therefore, you're actually making things worse. For all the things that serum's supposed to be making you sort of feel good, feel better, and sort of revitalise your body, could actually have a very detrimental effect. So it's not just useless, it can actually be dangerous. And that's the thing to watch out for. Any invasive thing you've got to be careful of, and something which is a pseudoscience, you have to be even more careful of.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.